Hello there, and welcome to Sleepy Science Vault. Somewhere out there, in the quiet dark between stars, there are objects so strange that even scientists spent decades struggling to describe them properly. Objects with no surface, no solid ground, no light of their own, just presence, density, gravity beyond imagining. Tonight, we're going to talk about black holes. But not the way most people imagine them. Not the swirling, screen-filling monsters from science fiction. Not the galaxy-devouring giants you might picture when you hear the phrase black hole. Tonight, we're going to talk about the smallest ones. The compact ones. The quiet ones. The black holes that, despite everything they contain, could fit within a space smaller than some cities, and yet still bend the fabric of space and time around them without effort. This is a journey into scale, into density, into the strange physics of things that are simultaneously enormous in mass and impossibly small in size. So if you're here to relax, to drift, to let your mind wander gently through the cosmos while your body settles into rest, you're in the right place. There's no need to follow every detail closely. Just let the information wash over you, the way starlight washes over a quiet field at night. Some of it will sink in. Some of it will simply become part of the atmosphere around you as you fall asleep. Let's begin. When people hear the term smallest black hole, there's often a small, natural misunderstanding. We tend to picture something almost invisible, a pinprick of nothing, drifting silently through space, small enough to slip between your fingers if you could somehow reach out and touch the fabric of reality. But that is not quite what astronomers mean. The smallest known black holes are still what scientists call stellar mass black holes. Not microscopic. Not delicate. Not something you could hold in your palm, even in theory. They are, in truth, collapsed remnants of stars. Objects born from the death of something far larger than our sun. Something that lived, burned, and eventually gave way to gravity itself. So when astronomers use the word small in this context, they are speaking in relative terms. Small compared to other black holes. Small compared to the giants that anchor galaxies. Not small in any way that feels intuitive to the human mind. This distinction matters, because it shapes everything else we'll explore tonight. When astronomers discuss the smallest black holes discovered so far, they are almost always referring to these stellar mass objects, not the theoretical microscopic black holes that appear in certain corners of physics, tiny hypothetical structures that may have formed in the extreme conditions of the early universe, if they exist at all. Those hypothetical primordial black holes are a separate mystery altogether, something for another quiet night, perhaps. Tonight, we are focused on real, confirmed, measured black holes. The ones that scientists have actually detected, calculated, and studied using light, gravity, and the subtle signatures they leave on the stars and gas around them. And among these confirmed objects, one holds a particularly fascinating title. According to data highlighted by NASA, the lightest known black hole currently identified has a mass of about 3.8 times that of our Sun. Let that settle for a moment. 3.8 times the mass of the Sun. Compressed down into something almost unimaginably small. To understand why that number matters, you have to understand what black holes actually are, and how they form. When certain massive stars reach the end of their lives, they can no longer sustain the delicate balance between outward pressure and inward gravitational pull. For most of a star's life, nuclear fusion in its core produces enough outward force to counteract gravity, holding the star in a kind of dynamic equilibrium. But when the fuel runs out, when fusion can no longer continue, gravity wins. The core collapses. For some stars, this collapse is violent and explosive, resulting in a supernova, scattering elements across space that may one day become part of new stars, new planets, even new life. But for stars massive enough, something else happens. The collapse doesn't just create an explosion, it creates a singularity. A point where matter becomes so densely packed that space and time themselves bend beyond ordinary comprehension. And that is how a black hole is born. The sun's mass, multiplied by nearly 4, crushed down into something almost beyond geometry. This brings us to one of the most fascinating real-world examples astronomers have studied, a system known as XTE J1650-500. It's not a name designed for poetry. It's a designation, a catalog entry, the kind of technical label astronomers use to keep track of countless objects scattered across the sky. But within that unremarkable string of letters and numbers lies something extraordinary. The black hole associated with this system was described as being only about 24 kilometers across. 24 kilometers. To put that into a gentler, more familiar measurement, that's roughly 15 miles. Now, pause for a moment and consider that number honestly. 15 miles is a distance many of us could drive in under 20 minutes. It's a distance you might casually cover on a long hike, or during an afternoon bicycle ride through a park. And within that modest span, enough mass to outweigh several suns combined has been folded into a region of space so compact, so dense, that light itself cannot escape its pull. It's difficult to fully absorb the strangeness of that. Our minds are built to intuitively understand things like size and mass together. We expect big things to be heavy, and small things to be light. But this is where black holes quietly break that intuition. Because when it comes to black holes, small does not mean lightweight. Small can still mean unimaginably massive, if the density is extreme enough. And here is where the numbers become almost hypnotic if you let them. Astronomers have found that the size of a black hole scales directly with its mass. This relationship is elegant in its simplicity. The more massive a black hole is, the larger the radius of its event horizon becomes. And the less massive it is, the smaller that boundary shrinks. So a black hole with only a few times the mass of our Sun can end up being just tens of kilometers across. Not thousands. Not millions. Just tens. A distance you could travel by car in less than an hour, and within it, a gravitational pull so powerful that nothing, not light, not matter, not even information as physicists understand it, can escape once it crosses the boundary. It's worth letting that idea rest in your mind for a while, not to analyze it intensely, but simply to notice how strange and quiet that truth is. The universe doesn't need enormous size to create enormous consequence. Sometimes, the smallest regions hide the most extreme physics of all. Now, it's important to gently correct a common misunderstanding that many people carry when they picture a black hole for the first time. Despite the name, black holes are not empty. They are not holes in the traditional sense. Not gaps. Not voids where matter has vanished into nothingness. They are, instead, extraordinarily dense concentrations of matter, compressed into an unbelievably small region of space. Imagine, for a moment, an object with the mass of several suns, not spread out gently across a glowing sphere millions of kilometers wide, the way our own sun exists, but instead pulled inward, tighter and tighter, collapsing under its own gravity until it occupies a space only a few dozen kilometers across. That is not emptiness. That is density beyond anything found naturally anywhere else in the universe. Scientists often describe black holes as regions where matter has been crushed, compacted, folded into a volume so small that ordinary physics starts to behave in extraordinary ways. It's a helpful reminder, actually, because so much of black hole mythology and popular culture leans on the idea of nothingness, blackness, absence, a hole in the truest sense of the word. But what's actually happening is almost the opposite. It's not an absence of matter. It's an overwhelming, concentrated presence of matter, so extreme that light itself cannot resist its gravitational pull. And this brings us gently to one final concept for this segment, a concept that will echo through much of what we explore in the hours ahead. The boundary of a black hole. The edge. The point of no return. Astronomers call this boundary the event horizon. It's not a physical wall. Not a surface you could touch, or a barrier you could see with your eyes, even if you were floating peacefully nearby in a spacecraft. The event horizon is better understood as a mathematical and physical threshold, a boundary in space where the escape velocity required to break free from gravity becomes equal to the speed of light itself. Beyond that point, nothing can escape. Not light, not radiation, not matter, nothing. Once something crosses the event horizon, it becomes gravitationally bound to the black hole in a way that no known force can reverse. This is part of what makes black holes so visually mysterious, even to astronomers using the most advanced telescopes in the world. We cannot see the inside of a black hole directly, because nothing, not even the light we would need to observe it, can travel outward once it has crossed that boundary. So what we see, instead, are the effects of a black hole's presence on the space and matter around it. The gravitational pull. The bending of light around its edges. The way nearby stars orbit, as if dancing gracefully around something invisible, something silent, something profoundly powerful. And that quiet paradox is part of what makes black holes so endlessly fascinating. They are among the most powerful objects in the universe, and yet, in a strange way, they are also among the most silent. No light escapes to announce their presence. No sound travels through the vacuum of space to reveal their location. They simply exist. Pulling, shaping, influencing everything nearby, invisible and unyielding. As we continue through this exploration together, we'll gently uncover more of these strange, quiet truths, one fact at a time, allowing each idea to settle softly into your mind, the way starlight settles over a sleeping world. For now, let this first understanding rest with you. Black holes are not empty. They are not holes in the way we imagine holes to be. They are the smallest regions in the universe, holding some of the greatest densities imaginable. And in the next set of facts, we'll continue drifting deeper into their mysteries, exploring how these compact objects form, how they behave, and what makes them some of the most extraordinary structures the universe has ever created. For now, let your mind rest here, in this quiet space between stars. And we'll continue soon. Let's continue drifting deeper into this boundary we touched on a moment ago, this strange, invisible line drawn across the fabric of space itself. Because the event horizon deserves more than a passing mention. It deserves real understanding, the kind that settles slowly, the way fog settles over a valley at night. At its simplest, the event horizon marks the point where escape becomes impossible. Not difficult. Not challenging. Impossible. Even light, the fastest thing in the universe, the thing that outraces everything else in existence, cannot escape once it crosses that line. Think about that for a moment. Light travels at roughly 300,000 kilometers every single second. It crosses vast distances in the universe with an ease that nothing else can match. It's the standard by which we measure the speed of everything. And yet, even light surrenders here. Once something crosses the event horizon, whether it's a photon of light, a stray particle of dust, or a wandering asteroid pulled too close, there is no return path. No trajectory. No amount of energy or force can reverse that journey. This is why astronomers often call the event horizon the point of no return. It's a phrase that sounds almost poetic, almost literary, but it's also precisely accurate, in the most literal scientific sense. There's no ambiguity here. No gray area. No partial crossing where something might slip back out if conditions were just right. Cross the event horizon, and that crossing is final. But here's something worth pausing on gently, something that often surprises people when they first learn it. The event horizon is not a physical surface. It's not made of matter. It's not something you could bump into, or touch, or see glowing faintly in the dark like the surface of a planet or the edge of a cloud. It is, instead, a boundary in space-time itself. A mathematical threshold, a point where the geometry of space and time becomes so warped by gravity that escape velocity exceeds the speed of light. If you were somehow able to approach a black hole safely, and observe the event horizon from a careful distance, you wouldn't see a wall. You wouldn't see a shimmering barrier or a glowing ring marking the edge. You would simply see darkness. A perfectly black, perfectly smooth region where light behaves differently than anywhere else you've ever known. It's a boundary defined not by texture or material, but by physics itself. This is part of what makes black holes so quietly humbling to think about. We are used to boundaries we can touch. Walls. Doors. Shorelines. Even the edge of the atmosphere, thin as it is, still contains something tangible. But the event horizon exists purely as a consequence of gravity bending the very structure of reality. It is, in the truest sense, the boundary you cannot cross back from, not because of a lock, or a barrier, or any physical resistance, but because the space itself curves so completely that all paths, quite literally, lead only inward. And this leads us naturally to something else worth sitting with quietly for a while. Because of the event horizon, black holes don't emit light of their own. They aren't like stars, radiating warmth and brightness outward for light years in every direction. They don't glow softly on the edge of a galaxy the way a distant sun might. In fact, in the most direct sense, black holes are invisible. Not invisible in a mysterious, mystical way, but invisible in a very literal, physical sense. Since no light can escape from within the event horizon, there is nothing for our eyes, or even our most advanced telescopes, to directly detect. You cannot simply point a telescope at a black hole and see it glowing in the dark, the way you might spot a distant star. So how, then, do astronomers find them? This is where the story becomes even more fascinating. Since black holes cannot be seen directly, especially the smaller, quieter ones scattered throughout our galaxy, scientists rely instead on indirect evidence. They study the gravitational effects black holes have on the things around them. A black hole might not shine, but its gravity still reaches outward, silently influencing nearby stars, gas clouds, and orbiting debris. Astronomers watch for these subtle signs. A star orbiting what appears to be nothing. A stream of gas being pulled and stretched into a glowing disk as it spirals inward, heating up from friction, and radiating X-rays that our instruments can detect. It's a bit like recognizing someone's presence in a dark room, not because you can see them, but because you notice the way the air moves, or the way objects around them seem to shift and respond, silently, as if guided by hands you cannot see. Small black holes, the stellar mass kind we've been focusing on tonight, are often discovered exactly this way. Not through direct sight, but through their gravitational fingerprints, left gently on the motion of the stars and gas surrounding them. Now, here's a thought that tends to surprise people the first time they hear it, and it's worth letting it unfold slowly. From far enough away, a black hole's gravity behaves exactly like the gravity of any other object with the same mass. That might sound strange at first. After all, black holes are described using such extreme language: crushing, warping, inescapable. It's easy to imagine their gravity as something uniquely terrifying, something fundamentally different from ordinary gravitational pull. But mathematically, that's not quite true. If you were orbiting a black hole from a safe distance, far outside its event horizon, the gravitational force you'd experience would be no different than the pull of a star, or a planet, or any other object with that same amount of mass. Gravity, after all, depends primarily on two things: mass and distance. It doesn't matter, gravitationally speaking, whether that mass is spread out across a glowing stellar surface millions of kilometers wide, or compressed into a compact sphere only a few dozen kilometers across. From far enough away, the pull feels the same. This leads us to one of the most calming, almost meditative thought experiments in all of astrophysics. Imagine, for a moment, that the sun, the warm, glowing center of our solar system, was somehow replaced, instantly, with a black hole of the exact same mass. No more sunlight. No more warmth radiating outward. No more golden light rising over the horizon each morning. Just darkness where our sun once was. It's a jarring image, isn't it? The kind of thought that might feel unsettling if you dwell on it too directly. But here's the calm, strange truth hidden within that scenario. If the sun were replaced by a black hole of equal mass, the planets would continue orbiting exactly as they do now. Earth would still orbit at the same distance. So would Mars, and Jupiter, and every other planet in our solar system. Their paths would remain unchanged, not because gravity would somehow soften or become gentler, but because gravity, at that distance, doesn't care about the object's size or appearance. Only mass and distance matter. A black hole with the same mass as the sun would exert precisely the same gravitational pull on the planets as the sun itself currently does. And so, remarkably, the orbits would stay the same. Of course, life on Earth would not survive such a transformation. Without the sun's light and warmth, our planet would grow cold and dark almost immediately. But the physics, the quiet mathematics governing motion and orbit, those would remain steady. Unchanged. Indifferent to the dramatic transformation happening at the center of it all. It's a strange kind of comfort, in a way, to realize that gravity, one of the most fundamental forces shaping our universe, doesn't discriminate based on appearance. It doesn't care whether the source of its pull is a bright, burning star, or a silent, invisible sphere of collapsed matter. Mass is mass. Distance is distance. And motion, guided by gravity, continues onward, steady and predictable, regardless of what lies at the center. As we continue moving through this journey together, we'll carry this idea forward gently, the idea that black holes, for all their strangeness, still obey the same fundamental rules that govern the rest of the universe. They are not chaotic anomalies, breaking the laws of physics. They are, in many ways, simply extreme expressions of the same laws that guide every planet, every star, every quiet orbit across the cosmos. In the next set of facts, we'll continue exploring these ideas further, moving gently into new territory, new discoveries, and new perspectives on just how small and how powerful these strange objects can truly be. For now, let your thoughts settle here for a while, drifting quietly alongside the steady, unchanging rhythm of orbits that continue, undisturbed, even in the presence of the darkest objects in the universe. And we'll continue again shortly. There's a particular kind of curiosity that black holes tend to attract, a certain fascination that often leads people's imaginations somewhere far beyond the actual science. And it's worth gently addressing that here, before we continue any further into their story. Because in popular imagination, black holes are often treated as something almost magical. Doorways. Shortcuts. Passageways to somewhere else entirely. Science fiction has given us countless versions of this idea over the years, characters diving into a black hole and emerging somewhere impossibly distant, an alternate galaxy, another dimension, perhaps even another universe altogether, folded neatly into existence just beyond the event horizon. It's a compelling image. Almost irresistible, really, when you consider how vast and mysterious space already feels. But it's worth saying clearly, and calmly, black holes are not wormholes. They are not shortcuts through space. They are not portals leading to other dimensions, other universes, or some hidden layer of reality tucked just beyond our own. This distinction matters, not to diminish the wonder of black holes, but to understand them more truthfully, because the real physics, once you sit with it, is arguably just as remarkable as any fictional version. Wormholes, in the way they're often imagined, remain purely theoretical. Mathematically, certain equations in general relativity allow for the possibility of structures resembling wormholes, bridges connecting distant points in space-time. But there's no evidence that black holes function this way in reality. No observed case of matter entering one and reappearing somewhere else in the universe. What we do know, with much greater certainty, is something quieter, and in its own way, more profound. Black holes are not exits. They are endings, in a sense. Points where our current understanding of physics reaches its limits, where the equations we rely on begin to break down under the sheer intensity of gravity. There is no known reappearance point. No other side. No hidden tunnel leading somewhere else. Just the singularity. The event horizon. And a boundary from which nothing that we understand can return. It's important to release that particular fantasy gently, the way you might set down a story you once loved as a child, in order to make room for something more grounded, more real. Because when you strip away the fictional shortcuts and portals, what remains is something arguably even more incredible. The actual formation of a black hole. A story rooted not in fantasy, but in the very real, very physical death of a star. Most stellar black holes, the kind we've been focusing on throughout this exploration, begin their story as massive stars. Stars far larger than our own sun. Stars that burn brighter, hotter, and far more intensely throughout their relatively short lives. These massive stars spend millions of years in a delicate balancing act, a constant tug-of-war between two opposing forces. On one side, gravity, pulling the star's mass relentlessly inward, always trying to collapse the star under its own weight. On the other side, the outward pressure created by nuclear fusion, the very process that causes stars to shine. For most of a star's life, these two forces remain in balance. Fusion in the core produces enormous outward pressure, holding gravity at bay, allowing the star to maintain a stable size and shape for millions, sometimes billions of years. But eventually, that fuel runs out. Massive stars burn through their nuclear fuel at an incredible rate, cycling through heavier and heavier elements as they age, until finally, they reach iron. And iron is where the process stops. Fusing iron doesn't release energy, it consumes it. Once a star's core becomes primarily iron, fusion can no longer produce the outward pressure needed to resist gravity. And so, gravity wins. The core collapses, suddenly and violently, in a matter of moments, after millions of years of stability. For many massive stars, this collapse leads directly to one of the most dramatic events in the entire universe, a supernova. A brilliant, explosive death, briefly outshining entire galaxies, scattering elements like carbon, oxygen, and iron out into space, the very same elements that would one day become part of new stars, new planets, and even living things. But for the most massive stars, something remains behind. At the very center of that explosive collapse, an incredibly dense core survives, continuing to collapse inward under its own gravity. If that remaining core is massive enough, it doesn't stabilize as a neutron star. It continues collapsing, past every known limit, until it becomes something else entirely. A black hole. This is the standard formation route scientists currently understand for the smallest known black holes. Not portals. Not cosmic shortcuts. Just the natural, physical conclusion of a massive star's life, an ending shaped entirely by gravity. Now, here's something that adds a quiet layer of mystery to this otherwise well-understood process. Astronomers have worked for decades to determine exactly how massive a stellar core needs to be in order to collapse into a black hole rather than settling into a slightly less extreme object, a neutron star. Current estimates suggest that there may be a minimum mass range required for this kind of black hole formation, somewhere around 1.7 to 2.7 times the mass of our Sun. Notice, gently, the uncertainty embedded in that number. Scientists don't state this range with complete confidence. They describe it as an estimate, a range still being refined, still being studied, still surrounded by open questions. In truth, astronomers still do not know, with total precision, the exact minimum mass a collapsing star can leave behind and still become a black hole. This uncertain area, sitting somewhere between the heaviest known neutron stars and the lightest known black holes, is sometimes referred to, quite poetically, as the mass gap. It represents one of the genuine unsolved mysteries still lingering at the edges of astrophysics, a quiet reminder that even with all our advanced telescopes, all our mathematical models, and all our accumulated knowledge, the universe still holds on to certain secrets, refusing to reveal them completely. And this brings us to one final, grounding piece of information for this segment. Objects with slightly less mass than that critical threshold, objects that don't quite reach the density required to become a black hole, are expected to become something else entirely. Neutron stars. These are, in their own right, extraordinary objects. Incredibly dense, though not quite dense enough to trap light the way a black hole does. A neutron star can pack more mass than our Sun into a sphere only about 20 kilometers across, an almost unbelievable density, though still governed by slightly different physics than a true black hole. The distinction between these two outcomes, a neutron star or a black hole, depends almost entirely on that delicate threshold of mass, a boundary the universe seems to draw with quiet, exacting precision, even if our current understanding of exactly where that line sits remains slightly blurred. It's a fitting thought to rest on for a while, the idea that even in something as extreme and violent as the death of a massive star, there is still a kind of quiet order at play. A threshold. A boundary. A line between one outcome and another, shaped entirely by mass, and governed by laws older than our Sun itself. As we continue moving through this journey together, we'll carry this understanding forward gently, the knowledge that black holes are not shortcuts, not portals, not doorways to somewhere else, but rather, the natural, physical conclusion of some of the most massive, most powerful stars our universe has ever created. In the next set of facts, we'll continue drifting further into this story, exploring more of what happens after collapse, more of what makes these smallest black holes so remarkable, and more of the quiet mysteries still waiting to be understood. For now, let this idea settle gently in your mind: the collapse, the threshold, the quiet boundary between one kind of stellar remnant and another. And we'll continue again soon. Let's turn our attention now to something that lies quietly at the very edge of what we currently understand about black holes, a boundary that scientists have been studying, testing, and refining for years. Because very small black holes are not simply a curiosity. They are not just an interesting footnote in the broader story of the cosmos. They are, in fact, scientifically important, precisely because of where they sit. These smallest black holes exist near the predicted lower limit for objects formed from the collapse of dying stars. They occupy a delicate space, right at the edge of that uncertain boundary we spoke of earlier, the line between neutron stars and black holes. And because of this, every small black hole astronomers discover becomes a kind of quiet data point, a small piece of evidence helping to refine our understanding of exactly where that boundary lies. Each one adds a little more clarity to a picture that has remained blurred for decades. This is part of why the story of XTE J1650-500 carries such weight within the astronomical community, even though, to most people, it remains a name they've likely never heard before tonight. Let's return to that system now, and explore it a little more deeply. The record for the lightest known black hole, as reported in 2008, belongs to this very system. XTE J1650-500. At the time, and even now, this discovery held particular significance. It represented one of the clearest examples astronomers had found of a black hole sitting right at the lower edge of what theory predicted was possible. The measurement itself placed the object at approximately 3.8 solar masses, though, as with most measurements in astrophysics, there was a margin of uncertainty attached. Scientists estimated the true value might vary by about 0.5 solar masses in either direction. This uncertainty isn't a flaw in the science. It's simply an honest acknowledgement of how difficult these measurements truly are. Astronomers aren't able to walk up to a black hole with a measuring tape. Instead, they rely on careful, layered calculations, interpreting light, motion, and gravitational influence from unimaginable distances away. And so, a small margin of uncertainty is not a weakness. It's simply part of what honest, careful science looks like. What makes this discovery even more remarkable is how it was made. The black hole in XTE J1650-500 was not identified through any direct observation of the black hole itself. There was no glowing surface to observe, no visible boundary to measure directly. Instead, astronomers identified it through what's known as dynamical evidence. In simpler terms, they didn't see the black hole. They saw its effects. They observed the way nearby matter moved, the way gravity shaped the motion of everything around that invisible point in space. And from those patterns, they were able to calculate, with remarkable precision, both the presence and the mass of the black hole hidden at the center of it all. This method, inferring the unseen through its influence on the seen, is one of the most elegant tools in all of astronomy. And it's made possible, in this case, by something particularly fortunate about this system's structure. XTE J1650-500 is part of what astronomers call a binary star system. This means the black hole is not alone, drifting silently through space in isolation. Instead, it exists in a close gravitational partnership with a companion star, the two of them locked together in a slow, continuous orbital dance. The black hole and the ordinary star orbit a shared center of gravity, each influencing the other's movement in a steady, rhythmic pattern. This binary structure turns out to be enormously valuable for scientific study, because it gives astronomers something visible to observe, the companion star, even when the black hole itself remains hidden from direct view. NASA has specifically highlighted this quality when discussing the lightest known black hole. Because it exists within a binary system, it becomes possible to study it indirectly, through the motion of its stellar companion. The logic here is quietly elegant. Stars don't typically move in isolation through space, at least not when paired with another massive object nearby. When two objects orbit a shared center of gravity, their motion becomes intertwined, each one subtly influencing the other's path. So when astronomers observe a star appearing to move in a strange, rhythmic pattern, almost as if it were gently orbiting something invisible, they immediately suspect the presence of a hidden companion. Something with enough mass to exert real gravitational influence, but without emitting any visible light of its own. Scientists sometimes describe this observable motion using a very human, very intuitive word: a wobble. The companion star doesn't move in a straight, undisturbed line through space. Instead, it appears to wobble slightly, tracing a subtle curved path that reveals the gravitational tug of something nearby, something unseen. This wobble becomes one of the most important tools astronomers use to infer the presence of a hidden black hole. By carefully measuring the star's motion, its speed, its orbital period, the shape and size of its path, scientists can work backward, using the laws of gravity, to calculate the mass of whatever invisible object is causing that motion. If that calculated mass turns out to be too great for a neutron star, yet the object itself remains completely invisible, emitting no detectable light, the most likely explanation becomes clear: a black hole. This is precisely how astronomers identified the small, quiet black hole hidden within the XTE J1650-500 system. They didn't see it directly. They couldn't. Its event horizon ensures that no direct observation will ever be possible, no matter how advanced our telescopes eventually become. Instead, astronomers studied the surrounding activity. The motion of the companion star. The behavior of gas and matter caught in the black hole's gravitational influence, sometimes forming a glowing disk as it spirals inward, heating up and emitting X-rays that our instruments on Earth are able to detect. Through this careful, patient method of indirect observation, astronomers were able to confirm both the presence and the approximate mass of this remarkably small black hole, one of the lightest, most compact examples ever measured with confidence. It's a beautiful demonstration, really, of how much can be learned about something we can never directly see. In a universe filled with vast distances and invisible forces, astronomers have developed patient, careful methods to reveal what lies hidden, not through direct sight, but through influence. Through motion. Through the subtle, gravitational fingerprints left behind on everything nearby. The black hole in XTE J1650-500 remains invisible, even now, to any telescope we might point toward it. And yet, we know it's there. We know its approximate size, its approximate mass, its location within that quiet binary system, locked in an endless orbital partnership with its companion star. All of this, learned not through sight, but through careful, patient observation of motion and light, gathered from unimaginable distances away. As we continue moving forward together, we'll carry this quiet lesson with us, the idea that even the things we cannot see directly can still be understood, measured, and known, if we simply learn to read the subtle signs they leave behind. In the next set of facts, we'll continue exploring further, moving deeper into the mysteries surrounding these compact, quiet objects, and uncovering more of what makes them such a fascinating part of our universe's story. For now, let your thoughts rest gently on that quiet wobble, that subtle dance between a visible star and its invisible companion, drifting endlessly together through the dark. And we'll continue again shortly. Let's continue this quiet investigation, peeling back another layer of the methods astronomers use to detect these hidden objects. Because the wobble of a companion star is only part of the story. There's another signal, more subtle still, that helped astronomers confirm what they were seeing in the XTE J1650-500 system. Something encoded not in the star's motion, but in the flickering, rhythmic patterns of X-ray light itself. Astronomers refer to this phenomenon as quasi-periodic oscillations, often shortened simply to QPOs. It's a technical term, admittedly, one that sounds more complicated than it needs to be. But the underlying idea is actually quite elegant once you slow down and sit with it. As matter spirals inward toward a black hole, it doesn't fall in smoothly, or all at once. Instead, it often forms a swirling, rotating structure, a disk of hot gas and dust caught in the black hole's gravitational pull, circling faster and faster as it moves closer to the event horizon. This structure is known as an accretion disk. And within that disk, something remarkable happens. Friction between particles, combined with the intense gravitational forces at play, causes the material to heat up dramatically. Temperatures can rise so high that the material begins emitting X-rays, a form of light far more energetic than anything visible to the human eye. But this emission isn't always perfectly steady. Instead, it often flickers, rising and falling in brightness and patterns that are almost rhythmic, though not perfectly regular. Almost like a heartbeat that isn't quite constant, subtly shifting from moment to moment. These flickers are the quasi-periodic oscillations astronomers study so carefully. By analyzing the timing, frequency, and pattern of these X-ray fluctuations, scientists are able to gather clues about the object at the center of that swirling disk, its mass, its size, even details about how closely matter can orbit before being pulled irreversibly inward. In the case of XTE J1650-500, these oscillations played an important supporting role, adding another layer of evidence alongside the companion star's motion, helping astronomers confirm both the presence and the approximate properties of the black hole hidden within that glowing, spiraling disk of matter. It's worth pausing here to appreciate just how much information can be gathered from something as seemingly simple as flickering light. A black hole itself remains dark, silent, entirely invisible, in the most literal sense. But the material surrounding it tells a different story. As gas and dust are pulled inward, compressed, and heated to extraordinary temperatures, they begin to radiate energy outward, light that our telescopes on Earth are able to detect and study, even from thousands of light years away. This is one of the most elegant truths in modern astrophysics. Black holes can be found by watching bright X-ray emission from hot material in their surroundings. The black hole itself may remain hidden, wrapped in absolute darkness, but its influence lights up everything around it, if you know how, and where, to look. This idea extends far beyond just XTE J1650-500. It's become one of the primary techniques astronomers use across the universe, watching for these signature X-ray emissions, then working backward, calculating the mass and characteristics of whatever invisible object must be causing them. Black holes, it turns out, can be invisible to ordinary telescopes, and yet still reveal themselves clearly, again and again, through their effects on nearby matter. It's almost like recognizing a storm not by seeing the wind itself, since wind has no visible form, but by watching the way trees bend, the way clouds swirl, the way loose leaves are lifted and carried through the air. You don't need to see the invisible force directly, you simply need to learn how to read its influence on everything around it. Now, let's shift our attention gently to another remarkable example, a discovery that captured public imagination in a particularly memorable way, thanks to its rather unusual nickname. Astronomers call this candidate the unicorn. Not because of anything mythical or fantastical about its nature, but largely because of the constellation in which it was found, and perhaps, in part, because of just how rare and elusive an object like this truly is. The unicorn was reported to have a mass of approximately 3 solar masses, placing it, remarkably, among the smallest known black holes ever identified. 3 times the mass of our Sun. Compressed down into an object so compact, so dense, that once again, our usual intuitions about size and mass simply don't apply. This black hole candidate was located roughly 1,500 light-years away from Earth, nestled within the constellation Monoceros, a name that, fittingly, means unicorn in Greek, giving rise to the playful nickname astronomers eventually adopted for this discovery. Despite that light-hearted name, the science behind this detection was every bit as careful and rigorous as any other black hole study. The unicorn was detected because it appeared to be gently tugging on a nearby red giant star, within a shared binary system. Once again, we see that same familiar method at work, the subtle gravitational influence of an invisible object, revealed through the motion of a visible companion. The red giant star, a massive, aging star nearing the later stages of its life, displayed a telltale wobble, a shift in its motion that couldn't be explained by any visible companion. By carefully studying this movement, astronomers calculated that an unseen object, with roughly 3 times the mass of our Sun, must be orbiting alongside the red giant, invisible, yet undeniably present. And given that mass, combined with the complete absence of any detectable light coming from the object itself, the most likely explanation, once again, pointed toward a black hole. What made the unicorn particularly notable, beyond its small size, was something else entirely: its remarkable proximity to Earth. At the time it was reported, the unicorn was described as the closest known black hole to our own solar system. 1,500 light-years might sound like an almost incomprehensible distance, and in many ways, it is. Light, traveling at nearly 300,000 kilometers every second, would still need 1,500 years to cross that gap. And yet, on the grand scale of our galaxy, spanning over 100,000 light-years from edge to edge, 1,500 light-years is, relatively speaking, right next door. It's a strange, humbling kind of comfort, in a way, to imagine a black hole existing in what amounts to our galactic neighborhood, quietly orbiting alongside its companion star, invisible and silent, yet close enough that astronomers were able to study it with remarkable precision. The discovery of the unicorn added another valuable piece to the broader puzzle astronomers have been assembling for years, another data point, sitting right near that uncertain boundary between neutron stars and black holes, helping to gradually refine our understanding of exactly where that delicate threshold lies. Each new discovery, whether it carries a formal astronomical designation like XTE J1650-500, or a more playful nickname like the unicorn, adds another quiet thread to this ongoing story. A story built not on direct observation, but on patient, careful inference, reading the subtle signs left behind by objects that will never be seen directly, only felt, through their gravity, and glimpsed indirectly, through the light of the matter and stars they influence. As we continue moving through this journey together, we'll carry this growing collection of discoveries with us, each one a small, quiet confirmation that even the most hidden, most elusive objects in the universe can still be understood, if we simply learn to listen closely enough to the subtle signs they leave behind. In the next set of facts, we'll continue exploring further, uncovering more of these remarkable discoveries, and moving deeper into the quiet mysteries that still remain unanswered. For now, let your thoughts rest gently here, on a red giant star, quietly wobbling in the dark, thousands of light years away, dancing endlessly alongside its invisible companion. And we'll continue again soon. Let's return once more to the unicorn for a moment, because there's a particular detail about its mass that deserves a little more attention before we move forward. At approximately 3 solar masses, the unicorn sat remarkably close to that uncertain boundary we've discussed, the delicate threshold separating neutron stars from black holes. This is precisely what made it such a valuable discovery. It wasn't simply another black hole, added quietly to a growing list. It was, instead, a kind of boundary marker, a real, physical example sitting almost exactly at the edge of what theoretical models predicted was possible. Every discovery like this helps astronomers refine that uncertain line a little further, narrowing the range, sharpening the picture, bringing a little more clarity to a boundary that has remained blurred for so long. And as it turns out, the unicorn wasn't the only candidate found hovering near that delicate edge. Some researchers have reported an even lighter candidate, with a mass of approximately 3.3 solar masses, found within a binary system known as 2-mass J05215658 plus 4359220. Yes, that particular name is, admittedly, quite a mouthful. a long string of numbers and letters, the kind of technical catalog designation astronomers often rely on when naming distant, faint objects discovered through automated sky surveys. But behind that complicated name lies another quiet, fascinating discovery, another possible black hole, sitting right near that same uncertain threshold, adding yet another data point to this ongoing scientific puzzle. Little by little, discovery by discovery, astronomers continue mapping the edges of what's possible, narrowing the uncertainty, one small black hole at a time. Now, let's shift our attention toward a related, and equally fascinating, question: proximity. Because so far, we've focused primarily on mass, on just how small these black holes can be. But there's another dimension to this story worth exploring gently: distance. How close, exactly, are these objects to us? NASA identifies a black hole known as Gaia BH1 as the nearest known black hole to Earth, located at a distance of approximately 1,500 light-years. This particular discovery, made using extraordinarily precise measurements from the Gaia Space Observatory, currently holds the distinction of being the closest confirmed black hole to our own solar system. It's worth noting, gently, that our understanding of closest and smallest continues to evolve as new instruments and new surveys uncover fresh data. Astronomy, in many ways, is a living, breathing field, constantly refining itself as new discoveries emerge. But what remains consistently true, regardless of which specific object currently holds the title, is this: the smallest known black holes tend to be much closer to Earth than the supermassive black holes we often hear about, the ones existing quietly at the centers of galaxies, including our own Milky Way. And yet, even at these comparatively close distances, measured in mere thousands of light-years rather than tens of thousands, or millions, these black holes are still detected indirectly. Not through direct imaging. Not through any telescope simply capturing a picture of the object itself. But through that same familiar method we've explored throughout this journey: gravitational influence. Subtle wobbles. Flickering X-ray emissions. The quiet, patient interpretation of indirect evidence. Even relatively nearby, on a cosmic scale, these black holes remain fundamentally invisible, revealed only through their effects on the universe around them. Interestingly, NASA has referenced another notable candidate in a rather unexpected context: a safety brochure, of all things, discussing black holes in an educational, approachable way for the general public. Within that brochure, NASA identifies 1A0620-00 as the closest known black hole, located at a distance of approximately 3,000 light-years. It's a gentle reminder that our understanding of closest can shift slightly, depending on the source, the timing of the publication, and which specific criteria are being used for comparison. Different missions, different datasets, and different points in time can sometimes lead to slightly varying answers, not because the science is inconsistent, but because astronomy, especially concerning something as elusive as black holes, continues to evolve and refine itself with each new discovery. Regardless of the exact distance measurement referenced, these objects, 1A0620-00, Gaia BH1, the Unicorn, and XTE J1650-500 among them, all share something remarkable in common. They exist much closer to us, cosmically speaking, than most people realize. And this brings us gently to another important, though perhaps less widely known, characteristic of smaller black holes, one that sets them apart in a meaningful way from their much larger, supermassive relatives. Smaller black holes produce noticeably stronger tidal forces near their event horizons, compared to supermassive black holes, even at similar relative distances. This might seem counterintuitive at first. After all, supermassive black holes contain far more mass, millions, sometimes billions of times the mass of our Sun. Shouldn't their gravitational effects be far more extreme? In terms of overall gravitational pull at a distance, yes, they are. But tidal forces work a little differently. Tidal forces arise from the difference in gravitational pull experienced across an object's length, the pull on one side of an object compared to the pull on the other side. Because smaller black holes have such compact event horizons, the gravitational gradient near their boundary changes dramatically over very short distances. This creates intense tidal forces, strong enough, in fact, that any object approaching too closely would be stretched and pulled apart long before ever reaching the event horizon itself, a phenomenon astronomers have given a rather vivid, memorable name: spaghettification. Supermassive black holes, despite containing vastly more total mass, actually have much gentler tidal forces near their event horizons, simply because their boundaries are so much larger. The gravitational gradient changes far more gradually across greater distances, meaning an object could theoretically cross the event horizon of a supermassive black hole without experiencing the same immediate, violent stretching. It's a strange, quiet irony that in some very specific ways, the smallest black holes can actually be more immediately dangerous, more intensely destructive at close range, than their far larger, more massive cousins. Now, let's turn our attention to one final concept for this segment, something deeply tied to the strange, fundamental nature of black holes themselves: time. Near any black hole, regardless of size, time behaves differently than it does here on Earth. This phenomenon is known as gravitational time dilation, a real, measurable effect predicted by Einstein's theory of general relativity, and confirmed repeatedly through both experiments and astronomical observations. In simple terms, time passes more slowly in stronger gravitational fields. The closer you are to a black hole, the more intense that gravitational field becomes, and the more pronounced this slowing of time appears, especially when compared to someone observing from a safer, more distant location. This isn't simply theoretical speculation. It's a well-established, thoroughly tested aspect of modern physics, one that even plays a practical role in technologies we use every day, such as satellite-based navigation systems, which must account for subtle differences in gravitational time dilation to remain accurate. Near a black hole, this effect becomes extreme. Time, from the perspective of an outside observer, would appear to slow down dramatically for anything approaching the event horizon, stretching out infinitely, at least mathematically, as that boundary is approached. And this leads us, finally, to the very heart of the black hole itself, a place we can only describe using theory, since direct observation remains, and will likely always remain, impossible. At the very center of a black hole lies something scientists refer to as the singularity. In standard descriptions, the singularity represents a point of infinite density, a place where all the mass of the collapsed star has been compressed down into an infinitely small point in space. It's important to approach this concept with a certain quiet humility, because the singularity represents the very edge of our current scientific understanding. At the singularity, our current laws of physics, the very equations that so successfully describe stars, planets, orbits, and even the event horizon itself, begin to break down entirely. Predictions become infinite, which in physics usually signals that our models are reaching their limits, rather than describing something physically real in the way we typically understand reality. Many physicists suspect that a deeper theory, one that successfully merges general relativity with quantum mechanics, will eventually be needed to truly understand what happens at the very center of a black hole. Until then, the singularity remains one of the most profound mysteries in all of physics. A place hidden forever behind the event horizon, forever inaccessible to direct observation, existing only within the quiet, careful language of mathematics and theory. As we continue moving through this journey together, we'll carry this sense of humble wonder forward with us, the understanding that even with everything we've learned so far, some of the deepest truths about these small, quiet, powerful objects still remain just beyond our reach. In the next set of facts, we'll continue exploring further, moving deeper into the remaining mysteries, and uncovering even more about what makes these smallest black holes such a fascinating, humbling part of our universe's story. For now, let your thoughts rest gently here, at the edge of a singularity, at the boundary where time slows, and space itself seems to fold quietly inward, beyond anything we can fully comprehend. And we'll continue again soon. We paused, a moment ago, at the very edge of the singularity, that quiet, mysterious point where our physics no longer knows how to speak clearly. Let's linger there just a little longer before moving forward, because it's worth restating gently, in slightly different words, just how profound this concept truly is. A black hole's singularity is the central region where current physics breaks down entirely. It's not simply a place that's difficult to study. It's a place where our equations, the very tools scientists use to describe nearly everything else in the universe, stars, planets, galaxies, even the event horizon itself, stop producing meaningful answers. Instead, they produce infinities. Numbers that spiral upward without limit, signaling not some strange physical reality, but rather, the outer boundary of human understanding. It's humbling, in the quietest possible way, to sit with that idea. To recognize that even now, with all our advanced telescopes and mathematical models, there remains a place at the center of every black hole that continues to resist true comprehension. But the story of black holes doesn't end there, because beyond the singularity, and beyond the event horizon, there are other behaviors, other characteristics, that continue to reveal themselves through careful observation. One of the most fascinating of these is spin. Black holes, it turns out, are not always still. Not always static. Many of them spin, sometimes slowly, sometimes with extraordinary speed. And this spin has consequences that ripple outward, quietly reshaping the space around the black hole itself. When a black hole spins rapidly, it doesn't just rotate in isolation. It actually begins to drag the surrounding fabric of spacetime along with it, a phenomenon that sounds almost impossible to imagine, yet is fully supported by both theory and observation. Picture, for a moment, a ball resting on the surface of a soft, stretched fabric. Now imagine that ball spinning rapidly in place. As it spins, it doesn't just rotate independently, it begins to twist the fabric around it, pulling and dragging the material along with its rotation. This is, in a very simplified sense, what happens around a rapidly spinning black hole. Space and time themselves become twisted, dragged along in the direction of the black hole's rotation. This effect, sometimes referred to as frame dragging, is one of the more subtle, mind-bending consequences of general relativity, a reminder that space and time are not fixed, rigid structures, but rather, flexible, responsive elements of the universe, capable of being shaped, twisted, and dragged by sufficiently massive, rapidly rotating objects. And when a black hole spins fast enough, this twisting effect becomes so pronounced that it creates an entirely distinct region of space, one with its own name and its own strange properties. This region is known as the ergosphere. The ergosphere forms just outside the event horizon of a rapidly spinning black hole, a kind of transitional zone, where the dragging of spacetime becomes so intense that nothing, not even light, can remain stationary within it. Inside the ergosphere, everything, without exception, is forced to move in the direction of the black hole's rotation. There's no way to resist this motion, no way to hover in place, no way to remain still relative to the distant stars. And yet, remarkably, objects within the ergosphere have not necessarily crossed the event horizon. In theory, it remains possible for an object, or even a spacecraft, to enter the ergosphere and still escape, provided it has enough energy and follows a very specific, carefully calculated trajectory. This distinction, between the ergosphere and the event horizon, highlights just how layered and complex the space surrounding a black hole can become, not simply a single boundary, a single point of no return, but a series of increasingly extreme regions, each with its own unique behavior and its own particular set of rules. It's a quiet, elegant reminder of just how much complexity can emerge from something as seemingly simple as mass, compressed into a small enough space, and set spinning fast enough to twist the very fabric of the universe around it. Now, let's shift our attention to another remarkable phenomenon associated with certain black holes, one that reaches far beyond the immediate vicinity of the black hole itself, extending outward across vast distances, sometimes even shaping the galaxies that contain them. Some black holes, particularly those actively pulling and surrounding matter, produce powerful jets of superheated gas. These jets form under extraordinary conditions, near the black hole's accretion disk, where intense magnetic fields, combined with the black hole's rotation, can channel a portion of the infalling material away from the black hole entirely, launching it outward instead, in two narrow, focused beams, extending in opposite directions from the black hole's poles. And these jets are not moving slowly. They travel at speeds approaching the speed of light itself, a staggering, almost incomprehensible velocity for something composed of actual matter, rather than pure light. These relativistic jets, as astronomers call them, can extend for extraordinary distances, sometimes stretching far beyond the black hole's host galaxy entirely, reaching out across thousands, even millions of light-years into the surrounding cosmic environment. Along the way, these jets can influence their surroundings in profound ways, heating surrounding gas, triggering new episodes of star formation in some cases, while suppressing it in others, and shaping the broader evolution of the galaxies that contain them. It's a striking image, when you allow yourself to sit with it quietly, a small, invisible object, hidden behind its own event horizon, somehow capable of launching matter outward at nearly the speed of light, influencing regions of space far larger than the black hole itself could ever directly touch through gravity alone. These jets represent one of the clearest examples of just how much influence a black hole can exert, not simply through its gravitational pull, but through the intricate, energetic processes occurring near its boundary. And finally, as we bring this segment gently toward its close, let's turn our attention to something far more theoretical, far more speculative, yet no less fascinating. Some of the tiniest black holes ever proposed exist not as confirmed astronomical discoveries, but as theoretical possibilities, objects known as primordial micro-black holes. Unlike the stellar mass black holes we've focused on throughout this journey, formed from the collapse of massive stars, these hypothetical micro-black holes may have formed under entirely different conditions, within the first fractions of a second after the universe itself came into existence. In those earliest, most extreme moments, immediately following the Big Bang, the universe was filled with intense density fluctuations, regions where matter and energy were compressed far beyond what we typically observe today. Some physicists theorize that, in certain especially dense regions, these fluctuations may have been extreme enough to trigger the formation of extraordinarily small black holes, objects potentially far lighter than any stellar mass black hole we've discussed tonight, some theoretically small enough to be measured not in solar masses, but in mere kilograms. It's important to approach this idea with appropriate scientific caution. No primordial micro-black hole has ever been directly confirmed through observation. Their existence remains, for now, a fascinating theoretical possibility, explored through mathematics and early universe cosmology, rather than through direct astronomical evidence. And yet, the idea itself remains quietly captivating, the notion that somewhere, scattered invisibly throughout the universe, there might exist black holes far smaller and far different from anything we've explored so far tonight, relics from the very first moments of cosmic history, silently drifting through space, their existence still waiting, perhaps, to be confirmed. As we continue moving through this journey together, we'll carry this sense of open curiosity forward with us, the understanding that even after everything we've learned so far, black holes continue to offer new layers of mystery, new questions, and new possibilities still waiting patiently to be explored. In the next set of facts, we'll continue drifting further into this story, exploring more of what makes these objects, both confirmed and theoretical, such an enduring source of fascination. For now, let your thoughts rest gently here, in that strange, twisting region just beyond the event horizon, where space itself bends and drags beneath the quiet, relentless pull of rotation. And we'll continue again soon. Let's continue gently where we left off, drifting a little further into that speculative territory surrounding the smallest, most theoretical black holes imaginable. Because while primordial micro-black holes remain unconfirmed, the possibility of their existence continues to occupy a quiet, persistent corner of modern astrophysics. Some very small black holes may have formed in the earliest moments after the Big Bang, but it's worth restating clearly and calmly that none have been confirmed. Not one. Despite decades of searching, despite careful mathematical modeling, and despite numerous theoretical proposals, no primordial black hole has ever been directly detected or verified through observation. This absence of confirmation doesn't mean the idea has been dismissed. Rather, it remains an open question, one of many quiet mysteries still lingering at the edges of cosmology, waiting patiently for either confirmation or refinement. What's particularly interesting about these hypothetical objects is just how different they would be from the stellar mass black holes we've spent most of this journey exploring. Even if primordial micro-black holes do exist, they would be fundamentally different from the known stellar black holes we've discussed tonight, primarily because of their potential size. While stellar mass black holes measure their dimensions in kilometers, tens of kilometers, in the smallest known cases, these theoretical primordial black holes could be almost unimaginably smaller. Some scientists theorize that certain primordial black holes might be microscopic in size, objects potentially comparable to the size of an atom, despite still carrying significant mass compressed into that impossibly tiny space. It's a strange, almost dizzying idea to sit with quietly. A black hole, with real gravitational influence, existing at a scale far smaller than anything visible to the human eye, even under the most powerful microscope ever built. And yet, once again, it's important to hold this idea gently, with appropriate scientific humility. These remain hypothetical possibilities, explored through theory and mathematics, rather than confirmed through direct observation. This leads us to perhaps the most extreme, most theoretical concept in this entire exploration of small black holes, a true, absolute theoretical minimum. Physicists refer to this smallest imaginable black hole as the Planck black hole, an object with a mass equal to what's known as the Planck mass. The Planck mass itself is an extraordinarily small unit of measurement, derived from fundamental constants in physics, constants that describe the very fabric of quantum mechanics and gravity together. A Planck black hole, if it could exist, would represent the theoretical boundary where our current understanding of physics reaches its absolute limit, a point so small, so extreme, that classical descriptions of black holes, and even much of general relativity itself, begin to lose their meaning entirely. At this scale, scientists believe that quantum mechanics and gravity would need to merge into a single, unified framework, something often referred to as quantum gravity, a theory that remains, even now, one of the most elusive goals in all of modern physics. Since no such unified theory currently exists, the Planck black hole remains entirely hypothetical, a mathematical boundary marker, rather than a confirmed physical possibility. It represents, in a quiet, almost poetic way, the very edge of what we can currently imagine, sitting right at the boundary between what physics can describe, and what remains, for now, completely unknown. Now, let's gently shift our attention back to something far more grounded, back to the real, confirmed stellar mass black holes that have formed the heart of tonight's exploration. Because so far, we've focused primarily on one formation pathway, the collapse of a single massive star, following the exhaustion of its nuclear fuel. But this isn't the only way stellar mass black holes can form. Stellar mass black holes can also form when two neutron stars merge together. This represents an entirely different, and equally fascinating, formation pathway, one that doesn't rely on a single star's death, but instead, on the dramatic collision of two already dense, already extreme stellar remnants. Neutron stars, as we discussed earlier, are incredibly dense objects in their own right, capable of packing more mass than our Sun into a sphere only about 20 kilometers across. When two neutron stars exist within a binary system, gradually spiraling closer together over millions, sometimes billions of years, they eventually reach a critical point, where their mutual gravitational pull becomes strong enough to overcome the remaining distance between them entirely. The result is a collision of almost unimaginable violence and energy, two of the densest objects in the universe, merging together in a matter of moments. If the combined mass of these two neutron stars exceeds that same uncertain threshold we discussed earlier, the boundary between neutron stars and black holes, the resulting merger doesn't simply create a larger, more massive neutron star. Instead, it collapses further, crossing that critical threshold, and forming an entirely new black hole. This process offers astronomers a second, equally valuable pathway for studying the formation of small, stellar mass black holes, one rooted not in stellar death alone, but in stellar collision. And this idea of collision and merger doesn't stop there. Because black holes themselves, once formed, are not necessarily permanent, isolated objects, destined to remain forever unchanged. Two black holes can merge together, forming an entirely new, larger black hole. This might happen, for instance, within a binary system containing two separate black holes, gradually spiraling closer together over immense stretches of cosmic time, much like the neutron star scenario we just explored. As these two black holes approach one another, their gravitational interaction becomes increasingly intense, until finally, they merge completely, combining their individual masses into a single, larger black hole. This merging process represents one of the most energetic events known to occur anywhere in the universe. And remarkably, we now have direct evidence that these mergers actually happen, not simply as theoretical predictions, but as confirmed, observed astronomical events. Because when two black holes merge, they don't do so silently. Black hole mergers can produce something known as gravitational waves, ripples that spread outward through the very fabric of space and time itself, much like ripples spreading across the surface of a calm pond after a stone has been dropped into it. These gravitational waves were first predicted by Einstein's theory of general relativity, over a century ago, though for decades, they remained purely theoretical, considered far too subtle and too faint to ever be directly detected. That changed, remarkably, in recent years, when scientists finally developed instruments sensitive enough to detect these incredibly faint ripples in space-time, traveling outward from black hole mergers occurring millions, sometimes billions, of light years away. Two black holes can merge, and in doing so, emit gravitational waves that travel outward across the universe, eventually reaching Earth, where sensitive detectors are able to capture and measure these subtle distortions in space and time itself. This discovery opened an entirely new window into the universe, allowing scientists, for the first time in history, to directly observe black hole mergers, not through light or X-rays, but through the very fabric of space-time itself, gently vibrating in response to these extraordinary cosmic events. It's a remarkable thought to rest on quietly, as we bring this segment toward its close, the idea that black holes, these dark, silent, seemingly isolated objects, are capable of producing ripples so profound, so far-reaching, that they can be felt, indirectly, across unimaginable distances, eventually reaching our own quiet planet, spinning gently through space, listening patiently for these faint echoes of cosmic collisions occurring far beyond our own galaxy. As we continue moving through this journey together, we'll carry this sense of quiet wonder forward with us, the understanding that even the darkest, most hidden objects in the universe can still leave behind traces of their presence, echoes, ripples, and signals, patiently waiting to be discovered by those willing to listen closely enough. In the next set of facts, we'll continue exploring further, moving deeper into the remarkable phenomena surrounding these smallest black holes, and uncovering even more of what makes them such an extraordinary, endlessly fascinating part of our universe's story. For now, let your thoughts rest gently here, amid the quiet ripples of space-time itself, spreading outwards silently across the cosmos, carrying with them the echoes of distant, ancient collisions. And we'll continue again soon. Let's turn our attention now to a slow, quiet process, one that unfolds not over years or centuries, but over timescales so vast they stretch beyond human comprehension entirely. Because black holes, despite everything we've explored so far, are not entirely permanent, unchanging fixtures of the universe. They can, in fact, lose mass. Very, very slowly. This phenomenon is known as Hawking radiation, named after physicist Stephen Hawking, who first proposed the idea in the 1970s, a concept that, at the time, radically challenged the previously held assumption that nothing could ever escape a black hole, not even in the smallest, most theoretical sense. The physics behind Hawking radiation is subtle, rooted deeply in quantum mechanics, involving the behavior of particles and antiparticles near the event horizon itself. Without diving too deeply into the mathematics, the essential idea is this: near the boundary of a black hole, pairs of particles can spontaneously form, briefly, out of the quantum vacuum of space itself. Occasionally, one particle from this pair falls inward, crossing the event horizon, while the other escapes outward, carrying away a tiny amount of energy, and, indirectly, a tiny amount of mass from the black hole itself. Over time, through this quiet, continuous process, a black hole gradually loses mass. But it's important to emphasize, gently, just how extraordinarily slow this process truly is. Black holes can lose mass extremely slowly through Hawking radiation, so slowly, in fact, that for any stellar mass black hole, this process would take far, far longer than the current age of the entire universe to have any noticeable effect. We're talking about timescales stretching not just billions of years, but numbers so large they become almost meaningless to the human mind, numbers that dwarf even the current age of the universe by many, many orders of magnitude. In practical terms, This means Hawking radiation remains largely a theoretical curiosity when it comes to the black holes we've discussed tonight, a fascinating, elegant piece of physics, but not something with any observable, immediate impact on the black holes currently scattered throughout our galaxy. While black holes lose mass with almost imperceptible slowness, they can also do the opposite, growing, sometimes quite significantly, over time. Black holes can grow by pulling in surrounding gas, dust, nearby stars, and, as we explored a moment ago, even by merging with other black holes entirely. This growth process can continue, gradually, over enormous stretches of cosmic time, allowing some black holes to grow far beyond the stellar mass scale we've focused on throughout most of this journey. Some black holes, through this slow, patient accumulation of mass, eventually become what astronomers call supermassive black holes, reaching masses of millions, sometimes even billions, of times the mass of our Sun. These supermassive black holes exist in an entirely different category altogether, compared to the small, stellar mass black holes we've spent most of tonight exploring. And remarkably, one of these supermassive black holes exists much closer to home than you might expect. At the very center of our own galaxy, the Milky Way, lies a supermassive black hole known as Sagittarius A star. This black hole anchors the gravitational center of our entire galaxy, an enormous, invisible presence, around which every star, every planet, every quiet corner of the Milky Way, including our own solar system, gently orbits. Sagittarius A** has a mass of approximately 4 million times that of our Sun. 4 million. It's almost impossible to hold that number fully in your mind, especially after spending so much of tonight focused on black holes measured in just a handful of solar masses. And yet, even this staggering figure, 4 million solar masses, is still considered relatively modest compared to some of the largest supermassive black holes discovered at the centers of other galaxies, some reaching billions of solar masses, dwarfing even Sagittarius A** by remarkable margins. Despite its immense mass, Sagittarius A** remains, in its own way, quietly hidden, located about 26,000 light-years away from Earth, tucked deep within the dense, star-filled core of our galaxy, obscured from direct view by vast clouds of interstellar gas and dust. And yet, much like the smaller black holes we've studied throughout tonight's journey, its presence has been confirmed, not through direct sight, but through its powerful gravitational influence on the stars orbiting nearby. Supermassive black holes like Sagittarius A** don't simply sit passively at the centers of their galaxies. They play an active, ongoing role in shaping how those galaxies evolve over time. Supermassive black holes at galactic centers can influence star formation, gas dynamics, and the overall structure of their surrounding galaxies, their gravitational and energetic influence extending far beyond the immediate region around the black hole itself, quietly shaping galactic evolution across enormous spans of cosmic time. It's a humbling thought, in its own quiet way, to consider that our entire galaxy, home to hundreds of billions of stars, including our own Sun, continues to gently orbit around this single, invisible, supermassive point of gravity at its center. This brings us, gently, to a broader reflection on why black holes, both small and supermassive, matter so deeply to our understanding of the universe as a whole. Black holes help astronomers study extreme gravity, because they represent some of the strongest natural tests available anywhere in the universe for Einstein's theory of general relativity. In laboratories here on Earth, scientists can only recreate relatively modest gravitational conditions, nothing close to the extremes found near a black hole's event horizon. But black holes provide something extraordinary, a natural laboratory, existing far beyond our reach, where gravity behaves in its most extreme, most revealing form. By carefully studying black holes, whether through gravitational waves, X-ray emissions, or the subtle orbital motion of nearby stars, scientists are able to test the predictions of general relativity under conditions that could never be replicated artificially here on Earth. Time and time again, these tests have confirmed Einstein's theory with remarkable precision, reinforcing our understanding of gravity, space, and time, even in the most extreme environments imaginable. And this leads us to one final, elegant technique, a method astronomers have used with particular success near the very center of our own galaxy. Black holes have been found, and studied, by carefully tracking the orbits of nearby stars over many years, sometimes even decades. Near the center of the Milky Way, astronomers have patiently observed a small cluster of stars, tracking their positions, year after year, watching as they trace out smooth, elegant orbital paths around, seemingly nothing at all. By carefully measuring these orbits, their shape, their speed, their precise gravitational influence, astronomers have calculated, with impressive precision, the presence and mass of the invisible object at the center of those orbits. Sagittarius A* itself. This patient, long-term observational method represents one of the most beautiful examples of indirect discovery in all of modern astronomy, watching, quietly and carefully, over many years, as stars trace their gentle paths through the darkness, revealing, through nothing more than their motion, the hidden presence of one of the most powerful objects in our entire galaxy. As we continue moving through this journey together, drawing ever closer now to the final chapter of tonight's exploration, we'll carry this sense of quiet awe forward with us, the understanding that black holes, whether small and stellar, or vast and supermassive, continue to reveal themselves patiently, gradually, through nothing more than their gentle, persistent influence on everything around them. In our final set of facts tonight, we'll bring this journey to its close, reflecting on everything we've explored together, and settling gently into the quiet, lingering wonder that black holes leave behind, long after the details themselves begin to fade. For now, let your thoughts rest here, among the slow, patient orbits of distant stars, tracing their quiet paths around an invisible, supermassive heart, hidden deep within the center of our galaxy. And we'll continue, one final time, very soon. We return, one final time, to that quiet, patient method we touched on a moment ago, the practice of tracking stars, year after year, watching their orbits trace slow, careful paths through the darkness. It's worth sitting with this idea once more, gently, as we approach the closing moments of tonight's journey. Because black holes, again and again throughout this exploration, have revealed themselves not through direct sight, but through influence, through motion, through the quiet, gravitational fingerprints left behind on everything nearby. Tracking a star's orbit over many years requires extraordinary patience. It requires astronomers willing to return to the same small patch of sky, year after year, decade after decade, carefully recording tiny shifts in position, gradually assembling a complete picture of an orbit that might take a decade or more to fully trace. This patient, careful method has revealed the presence of countless black holes across our galaxy, small stellar mass objects, and the supermassive giant anchoring our galaxy's very center. For decades, this indirect approach remained the primary tool available to astronomers. Gravitational influence, orbital motion, flickering X-rays. Careful, patient inference, built entirely on evidence, without ever truly seeing a black hole directly. And then, in 2019, something changed. For the very first time in human history, scientists released an actual, direct image of a black hole. Not a mathematical model. Not an artist's rendering, or a simulated visualization built from indirect data. But a real, captured image, assembled from actual observational data, gathered from telescopes here on Earth. This extraordinary achievement was made possible by a project known as the Event Horizon Telescope. It's difficult to overstate just how significant this moment truly was for the field of astronomy. For decades, black holes had existed almost entirely as theoretical constructs, confirmed indirectly, calculated carefully, but never actually seen. And then, quite suddenly, humanity had a picture. The black hole captured in that historic image was known as M87*, a supermassive black hole located at the center of a distant galaxy, approximately 55 million light-years away from Earth. 55 million light-years is a distance that stretches far beyond anything we've discussed so far tonight. It's a distance so vast that the light captured in that image had been traveling toward Earth for tens of millions of years, long before humans, or even our early ancestors, existed anywhere on this planet. And yet, despite that almost incomprehensible distance, scientists managed to capture a clear, detailed image of this black hole's shadow, a dark, circular void, surrounded by a glowing ring of superheated matter, caught in the final stages of its journey toward the event horizon. This achievement wasn't the result of a single telescope, however powerful. No single instrument on Earth could have captured an image of this precision, from this distance, alone. Instead, the Event Horizon Telescope project linked together numerous observatories from locations scattered across the entire planet, effectively transforming Earth itself into one enormous telescope, with a diameter equal to the size of our entire planet. By carefully synchronizing observations from multiple locations, and combining the data using extraordinarily precise techniques, scientists were able to achieve a level of resolution that would have been utterly impossible using any single telescope alone. It's a remarkable example of global scientific collaboration, researchers from many different countries, institutions, and cultures, all working together toward a single, shared goal, ultimately succeeding in capturing an image once thought to be entirely beyond our reach. That image, released in 2019, remains one of the most significant achievements in the entire history of astronomy, a moment where black holes shifted, permanently, from purely theoretical objects, confirmed only through indirect evidence, into something humanity had, at last, actually seen with its own eyes. As we bring tonight's journey gently toward its close, there's one final idea worth resting on quietly, a question that continues to occupy the minds of astrophysicists even now. Can black holes grow indefinitely? Or is there some ultimate limit to how massive a black hole can eventually become? Some theorists have argued that black hole growth may not continue forever, without limit. One particular study proposed something called a luminous accretion limit, suggesting that as black holes grow larger and larger, the physical processes allowing them to continue accumulating mass may eventually become self-limiting. This particular study estimated that this theoretical limit might exist somewhere around 5 × 10⁻⁻⁻ solar masses, an almost incomprehensibly large number, dwarfing even the largest supermassive black holes currently known to exist. It's worth holding this idea gently, as we do with so many of the more theoretical concepts we've explored tonight, not as settled, confirmed fact, but as an ongoing area of active scientific inquiry, another quiet mystery, waiting patiently to be better understood. And so, as we arrive at the final moments of tonight's long, slow journey together, it feels fitting to step back, to take in the full, quiet scope of everything we've explored. From tiny black holes, only a few dozen kilometers across, barely larger than a modest city, to the giant monsters that anchor entire galaxies, containing the mass of billions of suns, the search for the smallest black holes continues to reveal something profound about the universe we live in. It reveals where stars end, the quiet, final threshold where nuclear fusion gives way, entirely, to gravity's relentless pull. It reveals where gravity itself reaches its limits, bending space and time so completely that even light becomes trapped, forever, within an invisible boundary. And it reveals where some of the biggest mysteries in modern physics still begin, at the edge of the singularity, at the boundary of the event horizon, and within that strange, uncertain gap between neutron stars and black holes that scientists continue, patiently, to explore. Tonight, we've traveled quietly through this story together, from stellar mass black holes only 15 miles across, to the supermassive giant anchoring our own galaxy, from theoretical Planck black holes at the very edge of quantum physics, to the first real photograph of a black hole's shadow, captured at last, after decades of patient, indirect searching. And through it all, one quiet truth remains, resting gently beneath everything we've explored tonight. The universe is vast, almost incomprehensibly so. And yet, even within that vastness, patient observation, careful mathematics, and quiet curiosity continue to reveal its secrets, one small discovery at a time. Black holes, whether small or supermassive, nearby or impossibly distant, remain among the most extraordinary objects our universe has ever produced, dark, silent, and powerful, yet still, patiently, willing to reveal themselves, to those willing to look closely enough, and to listen carefully enough, to the quiet language of gravity itself. As you drift now towards sleep, let these images settle gently around you, distant stars, tracing slow orbits through the dark, quiet ripples of gravitational waves, spreading outward across the cosmos, and somewhere, far beyond anything we can see with our own eyes, small, silent black holes, continuing their endless, patient orbits through the vast, quiet darkness of space. Thank you for spending this time with me tonight, drifting slowly through the mysteries of the universe's smallest black holes. Rest well, and let the stars carry you gently into sleep.